Hello, I am Muhammad Ali. We will explain about dielectric heating. Before we go further, I will introduce our team member. First is me, Muhammad Ali Razmi. Second, we have Uzairi. Third, we have Aika Firdaus. And last, we have Chua Wei Xiong.
Assalamualaikum and a very good day. My name is Muhammad Zai, and today I will be presenting a brief introduction to high frequency heating, which is also commonly known as dielectric heating. This method of heating plays an important role in various industries, especially where traditional heating methods fall short. Okay, so what is dielectric heating? Dielectric heating is a process of heating non-conductive materials using high-frequency electromagnetic fields, typically in the range of 1 to 100 MHz. The principle behind this method is based on how polar molecules respond to a rapidly alternating electric field. When the material is placed between two electrodes, the electric field forces these molecules to rotate back and forth rapidly. This will cause internal molecular friction, and from the friction, it will then generate heat from within the material. On the next slide, I will explain to you what are the components needed for this heating method. Okay, so there are three main components that we need to consider when performing dielectric heating. Number one is high frequency power supply, which is to generate the required alternating field for the electrode. Second one is electrodes, two poles that is used to apply the field to the material. And last one is the material itself, which must be a dielectric or non-conductive material such as woods, plastic, or textiles. And that's it on the brief introduction of dielectric heating. Thank you.
Assalamualaikum, I am Muhammad Ali Razmi. I will explain part diagram of the dielectric heating. As you can see, this is a basic setup for high frequency dielectric heating. The system consists of two metal electrodes connected to a high frequency AC power source. A dielectric material such as plastic or wood is placed between the electrode. When the high frequency alternating current passes through the electrode, it creates a rapidly changing electric field. The polar molecule inside the dielectric material try to align with this changing field. As the field oscillate, this molecule continuously rotate back and forth. The molecule friction generate internal heat uniformly through the material, unlike conventional heating, which warm from the outside in. The result is rapid and volumetric heating, ideal for drying, gluing, or welding non-conductive material for the electric heating. Next, I will explain about the equivalent circuit and phasor diagram. First, as you can see, this is the electrical equivalent of the physical setup, where the dielectric behaves like a capacitor with some internal resistance due to the dielectric loss. The current you can see is split into two, which is first is IC, capacitive current due to the idle capacitor. Next is IR, resistive current due to energy loss, which cause the heating. As you can see in the circuit, the dielectric has a parallel RC circuit. The resistance represents dielectric loss, where this is the key for generating heat in the material. Next is a phasor diagram. A phasor diagram showing the phase relationship between the voltage and current. IR is in phase with the voltage. This is the heating component. And next is IC, is a 90-degree out of the phase voltage, representing the idle capacitor part. As you could see in the phase diagram, the phasor diagram visualizes how the total current lag behind voltage. Only the resistive component contribute to real power and heat generation.
Now I would like to explain about working principle. First is application of high frequency AC field. The material to be heated is placed between two metal electrodes. A high frequency alternating voltage is applied across these electrodes, creating a rapidly alternating electric field through the dielectric material. Second is polarization of dielectric molecules. Insulating materials such as plastic contain polar molecules. When subjected to an alternating electric field, these polar molecules try to align with the field. Since the field direction changes rapidly, millions of times per second, the molecules continuously rotate back and forth. Third is friction and internal heat generation. The molecular rotation causes intermolecular friction and collisions. This frictional resistance converts electrical energy into thermal energy and heating the material uniformly from within. Okay, that's all from me. Thank you.
So microwave equipment consists of a microwave generator, magnetron, aluminum tube, waveguide, metal chamber for batch operation, and a tunnel fitted with a conveyor belt for continuous operation. So how is it processed? When a high voltage that around 4000 volt is applied, then the cathode produce the free electron, which give up their energy to produce the rapidly oscillating microwave and direct it the waveguide by electromagnets. So the waveguide that reflects the electric field internally and it transfers to the heating chamber. So in batch equipment, the rotating antenna on fan is used to distribute the energy, or the foot may be rotated on a turntable. Then in continuous tunnel, the different sign of antenna is used to direct the beam of energy over the foot and is passed to the conveyor. The common frequency used in microwave oven are around 2.45 gigahertz mainly. Then that's all. Okay, so there's another application which we use RF heating, radio frequency. It is a same process. I mean, I cannot say same, but it's a similar process that using lower frequency, then the food is also passed between the electrodes and the radio frequency voltage, and is the voltage is applied across the electrodes. So both electrodes, the change of the orientation of water dipoles and the result in a very rapidly heating. So RF heating also allow the in the selectivity in the location of heating and accuracy in control. But the limitation, because due to the capacitive the formula of the capacitance C equals to epsilon A over D, the thickness of the foot is highly restricted by the distance between the capacitor plates.